Welcome. My name is Blair, and this video is about natural language processing and feature engineering. It was inspired by others who talked about what they learned this summer. And as it so happens, this summer I spent a lot of time trying to improve the performance of the large language model application within my organization. And this video sort of contains a nice set of some of the tools and techniques that I use to improve performance that I thought would be interesting to some of my viewers. I'm really thankful to be a part of the SureSpan group. This really goes beyond just using ChatGPT sort of in the web interface that we're all sort of used to these days. That's a shovel. I sort of work on the scale that you see there in front of you. I work on these big loaders. I'm moving around quite a lot of data with LLMs. And so you need to really understand the metrics of the data to be able to effectively deploy these LLMs at scale. So document similarity search is you want to sort of collect all your sort of organizations. So document similarity search is a very important step in being able to collect similar documents and then sort of pass off to a chat agent that could then be used for users. However, a lot of organizations, in the rush to get a project done, they have many projects, but there's no formal structure to these project directories. And it ends up sort of being like that drawer on the right that everybody has in their kitchen, that junk drawer you just toss stuff in, and it's very disorganized. And with AI, there's ways that you can sort of, after the fact, go on and straighten everything out so that you have nice organized data sets to be able to feed into different chat agents for different reasons. And sort of the techniques behind that have to do with document similarity search, where you're embedding the text of these documents and then comparing them sort of numerically in a latent space. So I can't use the documents they were using at work. They're quite sensitive operational documents, but the techniques are the same. And so I chose the history and the decline and fall of the Roman Empire. It's a publicly available text. And the two documents that we're going to try to sort of search and try to like separate mathematically is volume 1 and volume 6. Obviously, coming from the same person, the same era, they're going to have a lot of similarities, but the topic should be only very subtly different. This is a good challenge to see document similarities in action. So now we come to some of the code of the project here in GitLab repository. Again, the general process was that we took a chunk and then we embedded it in a vector. In this particular example from Edward Gibbons, I use a vector of 512 values. In practice, in the documents at work, I used about 3,000 values, slightly over 3,000 values. And OpenAI and other providers, they're up to like over 12,000 values for their embedding vectors. And as you grow in size, you're getting more and more subtle extraction of tone and content when you have these longer vectors. But for 512 values, size vectors were used for this project. And of course, you can't really visualize 512 dimensions. And that's why there's all sorts of methods to reduce the dimensions. And I particularly like the t-distributed stochastic neighbor embedding. And this is nice because it keeps the dissimilarity between any two data points the same while reducing the dimensions. And then you get nice little two-dimensional plots like this. And you can see two distinct clear clusters, volume 1 in blue sort of on the bottom, and then at the top there, volume 6 in red. When you're sort of working at scale, it's so important to have a very deep understanding about what's going on in these embedding vectors. And I've become a real fan of ensemble methods. I don't just trust one measurement. I want to use different metrics to really understand, because they all work slightly differently. So for this particular project, I used 4 different metrics: the principal component analysis, the correlation, k-means, clustering, and variance. And you can see they all pick sort of slightly different feature importance. But when you have multiple ones in the ensemble, you can see there on the left 4 different values within that vector are selected as being more important or having a greater effect on the predictive ability of which cluster is going to be there. Um, in the end, when I was actually doing this similarity search with thousands of documents, over about 14,000 documents, I used something called Facebook AI similarity search. It's a very well known similarity search that's used in production. Using this smaller example, I wanted to show how sensitive it is, even to within the first volume. And basically, what I'm asking it to do is I'm asking it to find different certain particular clusters and find ones that are close to it. So I said the target clusters are 3. I said I wanted to just do the first 2, just the first chunk, the second chunk, and the third chunk, on the assumption that other chunks are going to be quite low in the order, are going to be identified. And indeed, that's exactly what we see. Target document 1, it was close to number 4. Of course, number 2 or 3 are not there to even select. Document 2, of course, 4 and 5 were found, and document 3, 4, and 5 were found as well. So even with 512 values, I think that's a lot of subtlety there, that it can pick up even the order within the first volume. And this scales drastically, and it was very successful for our project, and to find like really specific documents within these huge network drives. Another way, if you have some labeled data, is a random forest classifier. Decision trees are great for this sort of thing. These sort of embedded vectors, or just these values. Decision trees can just sort them so well. And this can be generally, there's a lot of different methods to judge feature importance, but one of the most well-known one is the Shapley additive explanations. And you can see here, just as above as the ensemble method showed, that feature 472 is so predictive of which cluster, 1 or 6, any given chunk is going to be. LIME, the local interpretable model agnostic explanation, is a really good, because you can only use it. You can use it on one data point at a time, and sort of let that explain which cluster it's going to be in. And again, with this particular sample, this chunk from volume 6, again, feature 472 is again a really good indicator of which cluster it's going to be. Another thing I got really into to try to increase performance is text normalization. This is where you sort of make everything lowercase and take out punctuation and take out different words. So here you see 2 different, a weak and a strong text normalization in Python. They look like this. They're a bit different. This is the weak normalization, and the strong one has different stop words and all the punctuation and everything. Very textbook way you're supposed to do it. Here's sort of a visualization by normalization type. The Euclidean distance and the cosine similarity is 2 different types of ways that you can measure distance. I found, and in practice, Euclidean distance was a bit more effective, and you can see that weak. The weak normalization had a bit stronger values. It was able to sort of pick up on the differences between distance, the dissimilarity, a bit better than the strong. And so this was a really interesting characteristic that I wasn't expecting. My sort of guess or theory about why we saw better performance with weak text normalization is that I assume that the LLM providers are doing much more robust and sophisticated text normalization on their end, and that you don't want to over process it. But this is something to keep an eye on in the future. That is my presentation on natural language processing and feature engineering. Thank you so much for viewing.